Hello everyone. In this video, we are going to talk about torsion. So what is torsion? Torsion is basically twisting a straight bar, or we use the word shaft, okay, when you give it some torque, and typically on one side you have some torque and the other side it cannot rotate. Okay, so on one side there is a fixed support, on the other side there is a torque, and so it is subjected to twisting. Sometimes it might be fixed on both sides and get the torque in the middle. So you can see examples here when you're using your screwdriver and turning some kind of bolt or screw into some material, right? If this side stops, okay, so this side gets stuck and you're still trying to apply some torque to the handle of the screwdriver, and this part is gonna stop, not turning, that is where the twisting starts. By the time the whole screwdriver is spinning, there is no twisting. Twisting is a form of deformation, okay? So the material should deform. It's not a rotation. It's different from rotation that you had in rigid bodies. Rotation, the whole object rotates together. Deformation, some portion of the object rotates, the other portion doesn't. That is twisting. Or you can look at this other example of the famous Tacoma's narrow bridge, where the structure here is fixed on both ends, and then in the middle you have basically the wind coming in and creating this mode of torsion, which caused the bridge to collapse. So the thing that we're gonna study in this video are objects that are with circular cross section. You can show that if objects have cross sections that are symmetric with respect to the axis of the torsion, in this case this guy, then when the twisting happens, the cross sections do not change in shape. All it happens is they basically rotate each one about the axis of rotation with progressively bigger angles. So let's say if this side is fixed and this other side is applied a torque to, so this first, if you break down the shaft into a bunch of smaller discs, basically you can see the first one does not rotate. The next one rotates a little bit more linearly, increasing until this last one rotates the biggest angle. And by angle here, we are talking about the angle measured here radially, okay? So that one rotates the most, and then the other ones rotate the smaller numbers. We're going to see that. But the shape of this disc does not change. They stay the same disc with the same radius. They just spin in place. But if the shape does not have symmetry about the axis, like basically a square cross section, here clearly the distance of different points on this cross section are different from the axis, so it doesn't have symmetry. In this case, if you break down this bar into a bunch of smaller, basically cubes, correct, rectangular cubes, then you're gonna see that basically their shapes are going to be distorted. So you can see that the straight lines will not stay straight, and you see they start curving, and you're going to see cross sections like this, okay, something like that, as opposed to the square, and they're going to deform. So this is not what we're going to study, because that is more complicated. It needs its own separate video. What we are going to study is this one. So the cross section stays the same, and the other one is the radius does not change, and the angle of rotation between one end of the bar and the other end, what's the other assumption we have, we're gonna consider it to be small. So if that is a very large angle, then we cannot use linear assumptions here. Now that does not necessarily depend on whether it's circular or not. That's basically the second assumption. But if the cross section is circular, it helps keeping that angle smaller. If it's basically a cross section with no symmetry, then you're gonna get bigger twist, what we call the twist angle or angle of twist. So that will help as well. Now, So how do we describe this torsion mathematically? So the way we do it is, here we consider two lines all over this shaft, line PQ, and then when the torsion happens, assuming that this side is fixed, the other side we apply the torque, this line PQ now goes to this line PQ prime. Okay, so this is point P, and this is point Q, and this is point Q prime. So it moves, correct? It moves on an arc and comes to the point Q prime. Okay? And this angle between these two lines, we call it phi. So phi is the angle of torsion, the twist angle on the very other end of the shaft at length at x equal L. And we call it the angle of twist, which you measure it in radian. But as I said, between this end and the other end at arbitrary location x, if you look at, for instance, this endpoint, call it R, and this other endpoint, call it R prime, the radial angle between R and R prime is what we show by phi of x. And this phi of x is not as big as phi, but clearly bigger than 0. Here the angle is 0. So phi of x is a number between 0 to phi, and it depends on the location. Now, how does it change with location? We'll see. It's a linear relation in this case. But this is what we have right now. Okay, and this is the basically side view of this, where you go from Q to Q prime. The radius of the shaft is R, and the angle of twist is phi. Now, if we want to calculate the shear strain, the change in the angles in pure torsion, what we do is we look at basically a small element at location X. So we move to location X, we consider some small disk that you can see here, and this disk has a thickness of dx. And here is that same disk, just maximized, okay, magnified. And then you can consider two lines on it, line AB that you had before the twist, and it goes to line AB prime. And this angle, this longitudinal angle between them is your gamma, okay, that is your shear strain. And this angle that is measured in the cross section, that is your small twist angle d phi. And this radius is r, the length is dx. And so one thing you have to consider about this gamma is the same for the entire shaft or for an element. Because if you go back and look at this picture, if I zoom in, you can see that this angle here, this side angle, that angle is the same at all locations. Whether you look at it here, here, or here, anywhere you look at that angle is the same. Okay, on the surface, on the very outer layer of this shaft, that angle is all over the place, the same value, and that is gamma. Now, this gamma depends on the radius. So if we calculate that gamma at the outer radius at this end, that is going to be the maximum value. But if you go inside the shaft and calculate for similar lines, that gamma is going to be smaller. So this maximum gamma that happens at the biggest radius, we call it gamma max. Okay? Now, what is gamma max? Clearly, you can see that if I want to calculate gamma max in this case, it is equal to, because it's a small angle in radians, it's equal to the length of this arc, BB prime, divided by the original radius, which is AB. Now, how much is AB? It's the same as dx, of course. How much is BB prime? Well, if you look at BB prime in this other rectangle, this one, or this slice of the circle, it is equal to R d phi. So gamma max is clearly going to be R d phi over dx, right? Is going to be R d phi over dx. And this guy here, this d phi over dx, we give it a name, we call it theta. What's the name of this entity? It's called the rate of twist, which is the angle of the twist per unit length. You can see that d phi over dx. So this d phi over dx, we call it theta, so gamma max is r times theta. Now, if you look at this theta, as I said, if you look at the entire thing here, the entire shaft, let me go back to that picture I had up there. If you look at the entire thing in this picture, you can see that gamma max is what in this picture? And starting with this small angle that is going all over the shaft. Clearly, it's equal to this arc, q prime, divided by this, if you call this end P, divided by PQ prime, or PQ. Now, QQ prime, the radius here is R, the biggest angle is phi, so it's going to be basically R times phi, and the length of PQ is L. Now remember, gamma max was R times theta. If you just look at it down here, gamma max is R theta, but it's also equal to R phi over L. So from here, you see that theta is what? Is phi over L. And remember, this is the same as d phi over dx. So you see d phi over dx is a constant value. So you see that phi is a linear what? Function of x. Because the derivative of it with respect to x is a constant value. Phi is constant, L is constant. So clearly, phi of x is just a linear function. When we say phi changes between 0 to phi, it changes linearly. What was the function of it? Clearly, you can see it's phi over L times x. That's this function. At x of 0, it's 0. At x of L, it's phi. So this is phi of x, phi over L times x. Okay? Yes? So the phi angle changes linearly with position like that. And the shear strain gamma is R times that phi over L, or R times theta. Good. Now moving on. So as I said, we call that gamma max. Why? Because if we move inside this shaft and go to a radius rho that is less than R, then if we look at this gamma angle, clearly gamma, instead of being R times theta, is going to be rho times theta. Why? Because this length here is going to be rho times d phi, and this length is dx, so it's going to be rho d phi over dx, which is rho times theta. And rho is less than R, so gamma is going to be less than gamma max. So gamma at any point inside the shaft is going to be rho times theta as opposed to R times theta, which is this gamma max. Okay? So you see gamma also changes linearly. Gamma at this center is 0. As you move radially out, it gets bigger and bigger until it gets to R times theta. The function of it is rho times theta. So gamma is a function of rho, and it is rho times theta, correct? And so this is also a linear function. Good, the shear strain. Now, if the bar is made of linear elastic material and your level of stress stays within a linear region, then the shear stress is going to be the modulus of basically shear, the shear modulus, times the shear strain. G times gamma. Gamma was rho times theta in general. Okay, so you get G rho theta, or you can write it as rho over R tau max, where tau max happens at the radius R, and it is GR theta. So tau max is what? The maximum shear stress in this bar happens at the very end, okay, at rho equal R, and it is G times R times theta. And remember, theta was phi over L. Okay, so this is the maximum shear stress that you can have, which is on the outside, and inside tau of rho is clearly rho over r times tau max, or g rho theta. Okay, so the shear stress also starts at 0 here, and as you move on to the r, shear stress gets bigger and bigger. So if you have this disk and you want to plot the shear stress is 0 here, and as you get bigger, as you go to the outer radius, it gets bigger and bigger. So you have a linear profile like this. This is arbitrary tau of rho. Okay, it's a linear increase from 0 to the max at the biggest radius. So this is the value for the shear stress at any location or the max. What about the direction of the shear stress on any element? Well, for that, all we need to do is to apply a cross section. So let's say they have this simple shaft, which is applied to it a counterclockwise torque on this end, the other end is fixed. And they show you some small element, this green element, somewhere along the shaft. So at this location X, they show you this element and say, show me the direction of the shear stress on this element. Which direction is that? Well, in order to determine that, first, you're going to cut this shaft right at the location. Now, it could be at the left end or on the right end of it. So in this picture, it is cut on the right end. So you come here and you cut this element. And if you do that, then you're going to get two pieces, the left piece and the right piece. Here we can look at any of them. Let's look at the left piece. Now, if you look at the left piece, clearly this torque is the support torque. The torque that comes from the distribution of the shear stress on this red cross-section should generate a counterclockwise torque to keep this whole thing at equilibrium. Okay? Yes? So, if that's the case, and if we zoom in here and look at this, clearly the shear stress on this right side, on this edge, let me put some color on it, on this edge, which direction should it be? Well, clearly it should be the direction that matches this torque. And this torque at this point, if you draw it, at this point, you can see that it is downward. So on this right edge, the shear stress tau should be downward, and that is what you can see right over here. Look. It is downward. Now that's all you need. If that one is downward, on the other face it has to be upward. And remember, on these corners, if you watch one of my videos that I showed that tau xy equals tau yx, you know that to keep this element from spinning, this torque here has to be this way and this one has to be this way, so they cancel each other and there is no total moment about this element for spinning. Okay, so that's it. That is the direction of the shear, and all of these have to be equal to the same tau. What tau? That tau depends on the location. If it's on the outer radius, this is going to be basically your tau max. And the value of tau max, remember how much it was. It was GR times theta. Okay, or GR phi over L. The question is, how do we find phi? We'll see. But this is basically your distribution of stress and the direction of stress on any arbitrary element anywhere on this shaft. Now, the big question is, fine, we found all of this. Now, and this is the way, by the way, this is the way that this element will deform, okay? Because of these stresses, it's going to go like that. Now, the question is, when I apply this torque, what relation exists between this torque and the shear stress? Okay, because if I apply a bigger torque, I should have bigger shear stress anywhere in the shaft. So what relation exists between tau and T? Well, we say T is coming from all of the individual torques or moments that are coming from these shear stresses on this element. So what you do is you consider some small element here, dA, at distance rho, right, at radial distance rho from the center of the shaft. This is a side view. R is the maximum radius. This is my element, and on this element there is the torque T, or tau, sorry, and this tau is tau of rho, okay? This is my function, tau of rho, applied on that. Now, if I basically get the torque from this tau, and that is going to be some small dt, and then sweep this area with this small element and calculate all these dt's and add them together by an integral, that should be the total torque. So the question is, how much is this dt? Well, dt is rho times df, where f is the force that caused this tau, correct? Or the equivalent force to create this shear stress. So this is a basically parallel force, and rho is the distance. Now, how much is the shear force? Well, clearly it's equal to the tau at that location times the area, right? Force is stress times area, and this rho exists there, so it's going to be rho tau rho dA. Now, what was tau rho? Remember, we just had the formula for tau rho. It was g rho theta. Okay? Or the other way to show it, if you remember, it was, if you look at this other formula that we had, look, it was rho over r tau max. So this is either going to be g rho squared theta dA, or you can write it as I said, you can write it as rho over r tau max, and then multiply by rho. It is going to be rho squared again divided by r tau max and dA. Now, in either case, the term r and tau max come out because they are constant, or in this case, g and theta will come out, and the term that stays is going to be rho squared dA. This term is going to stay in the integral because when you move dA, rho changes with dA when you sweep the whole area. So your total torque is going to be tau max over r times integral of rho squared dA. And if you remember, this guy, this integral, is the polar moment, I about the axis, IP. This is the polar moment about the axis of the whole surface, I polar, times tau max over r. So from here, this is equal to t. Now, if from here you solve for tau max, you can see tau max is RT over IP. So this is the maximum shear stress based on the torque, based on the radius, and based on the polar moment of the cross section. So that is your tau max, and tau was tau max, right? Remember, it was tau max times rho over r. So if you multiply that by that, this r and this r would cancel. Tau is going to be t times rho over IP, as opposed to r. It's going to be rho, and remember, rho was less than r. So this is shear stress at arbitrary radius. This is shear stress at the max radius. Remember, so when I showed you this profile here, this tau max is TR over IP. This tau of rho is rho T over IP. Okay, and clearly rho changes linearly from 0 to r. Okay, so this is the most important formula that we have found so far. That if I know the radius of the shaft, calculate its polar moment of inertia, and I know the torque applied at that section, I can find the maximum torque, the maximum shear stress at that location. Okay? Now, if I want the theta, remember theta, based on this definition, theta was either phi over L Or if you look at this definition here, it was tau over g rho, right? Or tau max over gr. So for this tau max, I'm gonna replace it with TR over IP, and then that R and that R would cancel. So T over GIP, that is the shear rate, d phi over dx or theta. And if I want the angle of twist phi, I can find it from here as well. So you see this guy is equal to T over GIP. This is phi over L. So if I multiply both sides by L, you can find phi. Phi is TL over GI. And that is your second most important formula. The angle of twist for a specific case where T is constant and G and IP are constant. So this is the angle of the twist, and this is the maximum shear stress or the shear stress at arbitrary location. And this is the rate of twist. So these boxes, these three boxes, are the most important formulas that you have for shear. Everything prior to this you can just ignore, because what we care is relating everything to the applied torque at that location. And so these are the important formulas. Now, if somebody says, what is the shear strain, gamma? Well, all you need is to divide tau by what? By G. So clearly, if we want gamma, this is tau over G. So it is going to be T rho over GIP. Or if you want gamma max, clearly it's going to be TR over GIP. Right? So you can find the shear stress strain as well. So now that we have these formulas, let's go ahead and apply them to something. But two other very simple things very fast before we apply them to example. One is, if the shaft is pure circular with diameter d. Now you might say, you just said we're going to look at circular shafts. So what do you mean by circular? It should be circular, right? But not all the shafts that are under torsion are solid. Here we are talking about a solid shaft. So a circular solid shaft, because some shafts are hollow like this. They are tubes. Okay, for them, this formula is going to be a little bit different. So here, if it's solid shaft with diameter d, then maximum torque, maximum shear stress is coming from this formula. Remember, TR over IP. Now R is d over 2. And IP, the polar moment, is pi d to the 4 over 32. So if you simplify, the maximum shear stress is going to be 16t over pi d cubed. Okay, so you see the relation with d is 1 over d cubed. So if you make the shaft 2 times bigger diameter, the maximum stress drops by a factor of 8. But if you make the torque 2 times bigger, the shear stress gets 2 times bigger. Okay, so you see that. Now you might say, what if it was hollow? Well, for a hollow one, what you have is an outside diameter and inside diameter, di and do. In that case, R is going to be do over 2, and IP is going to be pi over 32 do to the 4 minus di to the 4. And you can plug them both into this formula. And in that case, you have a tau max and you have a tau min, and tau min is not 0. For a solid one, as I just showed you, the minimum shear stress here, tau min, is 0 at the center. But if a shaft is hollow, there is no center because this portion of it is hollow. So you're going to go from a tau min to a tau max. So if I draw the profile for that, at this location there is a tau min, and this location there is a tau max. Still is a linear relation, but you don't start at 0. So this is tau max, and this is what? Tau min. This is the distribution for a hollow tube. And you can show that for a hollow tube, the strength to mass ratio is better than a solid one. So if you want to get a smaller twist angle and a smaller stress, instead of making it solid, make it hollow and use the mass that went to fill inside here, put it on the thickness of the wall outside. So you can show that two shafts with the same mass, one hollow, one solid, this one has a lot better strength to mass ratio. Okay, and we can show that. By the way, similar to axial loading, where we defined an axial stiffness, for torsion, we can also define torsional stiffness. What is that? So if you consider a torsion spring, you know that if you apply a torque to it and it changes some angle, the torque to it was the spring constant K, or KT, times the change in the angle theta. So the spring constant for that was T over theta. Now in this case, the angle that you change is phi as opposed to theta, so it's T over phi. And remember, the formula for phi is this. So if you divide T by that, you gotta get GIP over L. Okay, remember for axial loading, it was what? It was E and then A over L. That was axial stiffness or spring constant. This is torsional spring constant. You see in both of them, L is in the numerator. So shorter elements will have better stiffness. And instead of E, we have G because that was axial loading. This is torsional loading. And we had A for geometry. Here we have IP for geometry. So you see they are very, very similar. Okay, now that we have seen all of this, it is time to look at one real-life example of torsion. Where would you see that? One very common example, as I said up there, and it is valid here, is when you are turning and tightening a bolt or a screw. If this side stops rotating and you're trying to rotate on the other side, that's where you get the torsion and the twisting. And that can happen a lot with drill drivers. So here we are drilling into a block of wood or block of metal or something, and you probably experienced that if you work with drills, that especially if you are applying a lot of force to drill, you see at some point the drill bit stops spinning. While the motor is applying a lot of torque and wants to move forward, the drill stops, and we call it stall. For motors, we call it stall. So that T could be your stall torque that you're applying. The motor basically cannot turn anymore. And under that case, this side is fixed because it is inside the material, cannot move. This other side of it, you're applying the torque and you're trying to twist it. So that's where the torsion happens. Now here we assume that the drill bit diameter is 4 mils and the resisting torque from this material is 0.3 Newton meter. You want to know what is the maximum shear stress in the drill bit? Then if the allowable shear stress for the drill bit based on this material is 32 megapascal, how much should the stall torque be before you start breaking and deforming the drill bit? And then you want to know if the G for this material is 75 gigapascal, then what angle of twist or what rate of twist in this case would the drill bit go through? Okay, so there are 3 cases. Now remember, for the part A, we have the formula that we just derived for a solid shaft. We found that tau max is 16d over pi d squared. So we are going to use that, d cubed, I'm sorry. So we have all the numbers, right? That is 16, that is 0.3, this is pi, and diameter should be converted to meters. So it's 0.004 meters cubed, and you can get your maximum shear stress in Pascal. Okay, or if you leave it in millimeters, that is going to be megapascal. Okay, it's going to be this much megapascal. Now, I have to correct myself. I said if you leave it as 4, it's going to be mega, it's going to be gigapascal, because this is going to be 10 to the negative 9. Going to the numerator is going to be 10 to the 9 or gigapascal. If you just use 2 of the zeros, then it's megapascal. But anyways, if you simplify it, you're going to get 23.78 megapascal maximum shear stress. And actually, this was 87, not 78. So that is part A. Now, for part B, It's the opposite. The maximum torque is given. You want to find the maximum torque. The maximum tau is given. So tau max in this case, which is the same as tau allowed, is equal to 32 megapascal, and this is equal to 16t over pi times d cubed, and you can find t in this case. And you see that the shear is linearly related to the torque. So if I divide this number by this one and multiply it by 0.3, that's all I need for the torque, right? So 32 divided by that times 0.3. Look here. So 32 divided by this 2387, and then this is multiplied by 0.3, and you see 0.402. Newton meter. This could be the stall torque. Anything more than that, if the material resists more than that, you are gonna start breaking and deforming the drill bit. Okay, now for part C, it is asking for theta, and we can also find phi. So theta was T over GIP, and phi was theta times L, which is TL over GIP. Okay, now in this case, the L is not given. The length of this guy is not given, and by the way, it's variable as you drill into the part. So we cannot calculate this because L is not given, but we can calculate this guy, T over GIP. And the thing is, what T to use? If you use the T from case B, so this is 0.402, and this is 75 times 10 to the 9. That was gigapascal. And IP, remember, it was pi over 32 d to the 4. So it was this guy, correct? So that is all we need to calculate, and let's get this number. And this is the number that you will get. Remember, this is d phi over dx, so it is radian per meter. Okay, and that is the rate of twist. Now, if we had L at any point, we can multiply and we can get how much this end is fixed. This other end will basically go through how much of rotation. But in this case, it's not given. So this is the first example. Now, before we go to second example, there is another thing we have to look at, and that is if a shaft consists of multiple segments, each with different G, T, or IP, then if you want the total twist angle, you have to use the formula that we just showed you, TL over GIP, correct? Let's go up a little bit. So this one here, you have to use this formula, but you do it for each section and then add all these angles together. So if you are using some shaft, right, and this shaft has a shoulder in it, so it goes like this, and let's say this end of it is fixed, this other end you apply a torque, then clearly this section has a different diameter than this one. So this is IP number 1, this is IP number 2. Now, if there are two different metals that are welded together, then each one has its own G. And each one could have its own L. So this is L1, this is L2. They don't have to be the same. And if there is some support here, like a bearing or something, okay, now bearing does not apply a torque, so it's not changing the torque. But if there is any support here that will make the torque to change from here to here, the twisting torque, not bending moment, then you have to calculate that individual torque as well, and then add all of these individual phi's together to get the total phi. This is very similar to the formula that we had for axial deformation. Delta was summation of basically Fi Li over Ai Ei. Remember? That was what we had for axial deformation. The total axial elongation was this. And here is very similar thing. And remember back then we said if these changes in any of these four properties, especially these three, I mean, they don't happen with a sudden change, they happen gradually. So if you have like a conic shaft or something, then in this shaft, IP is not constant, it's a function of location. In that case, you cannot add these individual terms, you have to integrate, and that is what you can see here. Phi is equal integral from 0 to L of G, IP of X, T could be a function of X or could be constant, integral from 0 to L. Okay, so if you want to find phi for a conic shaft, you clearly have to find IP as a function of location, and then you integrate that. Okay? The last formula we need to look at is power transmission. So you know when you're transferring power through a motor and through gears to another system, through this motor, you are putting so much power behind this shaft. Now this shaft is spinning with some RPM omega, and through the gears, you are passing some torque to another gear that is going to another shaft. And you know the relation between power, omega, and T is P equals T omega. And omega, you can write it in terms of RPM, so you can write it 2 Pn over 60. That is your omega, where this N here is the RPM of the shaft as opposed to radians per second, which is omega. So this formula gives you the relation between power, torque, and the RPM. Now, if you want it in the British system, you can write it like this, where this is in pound, basically force feet. This is still RPM, but this guy is going to be in horsepower, as opposed to this guy, which is in watts. Okay, so you can use this one for British system, this one for the SI system. Okay, and we're going to see the application right here. So look at the example. You have a motor driving a solid circular shaft with diameter D. It is transferring 40 horsepowers to the gear at location B. So the power coming from this motor is 40 horsepowers. The allowable shear stress in that shaft steel is 6,000 psi. What diameter should you design the shaft such that you can operate the system at 500 RPM? What about if you want to drive it at 3,000 RPM? Right? So this is a design problem. What shaft diameter should we consider so we can pass so much horsepower at so much RPM from a motor and a gear to another system while this material is already selected. Now in the design, sometimes the material is not selected. You have to consider both geometry and material. And then you pick one of them, you go for the other one. But many times your material is limited and you pick the good material and you look at the diameter depending on what variations you have. I mean, do you have a limited space for the shaft? What are the other things? Okay, and then there is the vibrations of this shaft coming, which is not the topic of this video. And there are so many other things that for a simple shaft selection you have to consider. So in this case, we have to go with this top formula because it is in horsepower. So it is 4D and it is equal to 2 pi. And here I'm looking at part A, and N is the RPM, which is 500 times the torque, which I don't know, and divided by 33,000. So from here, you're going to get the torque to be 420.17 pound-force-feet. Okay? Now this torque is equal to what? If that is your torque, you can calculate your maximum shear stress, tau max, which in this case is the same as tau allowed. And this is equal to tau max is T d over 2, remember, pi, or if you want to use that formula that we derived, remember, we had this maximum thing, 16t over pi d cubed. We can use that because it's solid. So this should be equal to 6,000 psi. Now remember, this guy is pound force feet. And if you consider this in inches squared, and this is pound force per inch squared, you are mixing unit. And this is inch cubed, not inches squared. So I go ahead and multiply this by 12 to convert it to pound force inches. And this t, remember, is this number, so I can plug it right there. And from here, I bet you can calculate d to be 1.62 inches. This is the minimum diameter you need so you can pass that power at the given RPM without breaking the material. Now for part B, it's very similar. The only thing you are changing is basically that RPM. So you change this to 3,000 this time. Okay, that means your torque is going to be a 6 of what it was. So torque is going to be that number over 6. And from here, you can see that since d cubed is proportional to t, so d is going to be this third root of 6 times whatever it is right now. You get 2.94 inches for diameter, and so you can see that d is proportional to the cubic root of t, or inversely proportional to the cubic root of omega. Hopefully you learned something about torsion in this video. I'll see you in the next lecture. Thanks.